Okay, so before we continue, let me clarify something here about this concept of percolation threshold and this equation. For me to do that, let me open a whiteboard. So here we have, imagine I have two particles that are, one of them is here, and the other one is, and the other one is here, and the other one is here. So we have a spacing between them, and we mentioned an exponential function that describes the resistivity between them. And so basically we had resistivity that was proportional to exponential of s over S0. So then that adds another variable here. What S should be put here? Because if you choose different S's, the percolation threshold will change. But the answer to that question lies in the fact that, first of all, in this model, it's assumed that S is 0. So basically, when we are talking about contact, we are talking about a scenario in which carbon nanotubes are like that. They're almost touching each other. So basically, this is not there. Basically, this distance is 0. Okay. Now, so if the theory was true, in that case, the conductivity, if I wanted to plot, conductivity as a function of volume fraction, I would have obtained, so if this was conductivity, I would have obtained 0, 0, 0, 0, 0 conductivity. When the volume fraction, when the percolation threshold is reached, a jump, and then this. In reality, a jump, and then this. In reality, what we see is something more of this sort. Basically, the rise happens like that. The rise happens within a bound like that. Okay, and so, but it's a rather narrow bound, and that's because we start, although it's an exponential function, but it's not a step function. So there's a graduation to it. There's a gradual increase to it. What also you have to keep in mind is that this S, if in reality, if S is more than even 1 nanometer, the conductivity between those particles is almost 0. It's very, very low. So now 1 nanometer, most nanomaterials are way larger. The length of them is way larger than 1 nanometer, hundreds of nanometers. So with respect to so adding that 1 nanometer to spacing between nanofibers will not change the excluded volume by a whole lot. This is an explanation that I really want you to understand, because it can really be confusing. So going back to the equation for percolation threshold, so basically we calculate percolation threshold as the ratio of these two, and it gives us an equation like this. When we simplify it and take away second order functions like assume the aspect ratio is very high, we get an equation like this. Here, A is the aspect ratio of the particle. A is L over 2R. And here, instead of sine gamma, we put the average value of sine gamma because we have particles with different orientations. And so now let's consider a few cases when we have all parallel fibers, then theta or gamma is 0. So percolation threshold becomes 1/8, 12%. That's the case where all of them are aligned. Now, the case that all of them are randomly oriented, in that case, we will have the average value for sine gamma is pi/4, and we can get a different equation, so which I'm going to write it for you. So in this case, the equation we will be dealing with will be 1/8 is here plus 2a times pi/4 divided by pi. So it's going to be a divided by 2. And what is aspect ratio of most nanomaterials? Hundreds, thousands, tens of thousands. So this is going to be approximately 2/a. Okay, so basically the higher the aspect ratio of the particles, the sooner the conductivity, the sooner the percolation threshold will be reached. This is a real case example of volume conductivity or conductivity as a function of concentration. Look at the order of magnitude difference in from here to here is about 10 orders of magnitude difference, whereas volume fraction has gone up only 2.1%. Now, the aspect ratio of the carbon nanotubes in this case was rather very high. It was, basically the length of individual carbon nanotubes was maybe 10 microns or so. And so if you go with this equation, the percolation threshold should be way lower than 0.05%. So basically we can quickly do a calculation. So the length of, if I take the 10 micrometer, so the aspect ratio I am talking about is going to be radius of about 0.7 microns, so roughly about 1.5 nanometers. And so here we are talking about 10,000 divided by about 1.4. And so this, so basically 2/a, which is the percolation threshold, in this case will be 0.028%, right? And the reality is that this number is still, it's low, but in experiment, what we're getting is percolation threshold is higher than that. So basically, we needed more carbon nanotubes to percolate this network. And the reason for that is that any nanomaterial has a lot of surface area. And so basically, they like to agglomerate. They like to touch each other, okay? And every time you have some agglomeration, you're reducing the aspect ratio. That here, one particle, aspect ratio is 10,000 divided by 1.4. If you have 7 of them agglomerated like that, obviously it's an ideal model, but just for a thought process, it's very helpful. Then the length is still 10 microns. The diameter now is 2.1. So the aspect ratio dropped significant. Now, if you have more agglomeration, you will have even lower aspect ratio, which means you need more of the whole particles to percolate the network. And the reason you can understand this is that these particles are kind of over touching each other. You don't need this much contact to transfer electron from one to the other. And so when you have too much contact here, it means you're getting it from somewhere else. And so that somewhere else has lower number of carbon nanotubes that it needs to percolate if you're at this volume fraction. which means you need to be at higher volume fraction for it to percolate. So I am going to stop here and continue in the next slide.